Hello everyone, welcome to our discussion of section 2.2 where we will be continuing our discussion of the derivative. Now in this particular section we will be talking about differentiation and its various notations. We already introduced the one notation for it, which was the f prime of x. So if the original function is called f of x, then one notation to represent its derivative is called the f prime of x. Also, we have other notations that we can use, and we will be discussing those. Another topic in this section is where is a function differentiable? In other words, if differentiation is the process of finding the derivative, then where is a function differentiable or not? We will be talking about that. We will be also talking about the connection between differentiable, when a function is differentiable and when a function is continuous. So there's a connection between differentiability and continuity of a function. So that will be another concept we'll discuss. And also we'll be talking about higher derivatives. So we've talked about the first derivative, or f prime, but we do have higher order derivatives such as f double prime and f triple prime. So the second derivative, the third derivative, and the fourth derivative, and so on. We have those higher derivatives, and we will be talking about those with examples as well. So let's start with the differentiation and its various notations. You already have a pretty good idea from the last section about what differentiation is. So let's just recuperate that discussion very quickly, what we talked about in section 2.1. So recall that a derivative can be obtained by its definition. Remember that? When we use the definition of a derivative to obtain the derivative, can be obtained using the definition of the derivative as follows. So we looked at several versions of it. So it's the same concept, but there are various representations of it. So this was one of the presentations we talked about. We talked about f prime of x, right? So f prime of x equals limit as h goes to 0 of f of x plus h minus f of x divided by h. Remember that? We talked in section 2.1 about this. So that's one way of obtaining the derivative of a function. Another one was this form, which is the same formula or the same definition, but represented differently. So, and that is f prime of x equals limit as delta x goes to 0. Delta x, h really represents this delta x, right? The difference between two x values as they approach 0. So as the difference between two x values approaches 0, that's also what we mean by h. H represents that. So then f of x plus delta x minus f of x divided by, of course, delta x. Okay, so these are equivalent forms, but with different representations. Instead of h, you have delta x, which represents the same thing. And let me just, for the sake of clarity, I say that delta x is equal to the diminishing difference between two x values, or values of the independent variable, no matter what you call it. We usually call it x, but you can have other names for it, of course. So delta x would be, that's why you see this notation, this diminishing difference really is what we mean by this delta x going to 0. Okay? So that's what delta x is, that as that difference approaches 0, and delta x, we want to take this smaller and smaller and smaller, this delta x. That's why we're taking the diminishing difference between two x values. We also can represent this same concept, same definition, in a more concise or compact form, but saying the same thing. Right, so if we say f prime of x is equal to limit of delta x approaching 0 as delta y divided by delta x. So we take this difference in the numerator as delta y. Right, it represents that difference. Delta y represents the difference in the y values. Okay. So this process, when we go through this process of calculating this derivative, this process is called differentiation. So let's write that down. I'm sure you already had thought of that, but just for the sake of your notes, we're going to write this down, that the process of obtaining the derivative is called differentiation. Okay. And the meaning of it, of course, we talked about this in section 2.1. But why not, since we've just introduced it, why not mention it again here, that, so obtaining the derivative, and the derivative, of course, is the slope of the tangent line. And the slope of the tangent line to the function at some particular point, some particular point, okay? And we've already talked about these, so we might, I just want to, so this was all just a recapping of what we've already learned in section 2.1. So we also said that we're going to talk about the various notations, right? So let's talk about that. Very, very important, especially for those of you who will be taking the complete series of calculus, going up to calculus 2, 3, and also the differential equations course later on. So you're going to need to know these different notations by which we represent derivatives, and so that you, when you see them, then you'll know what they are. Okay, so that's that. All right, so we're already familiar with one form, right? We know that f prime x is one notation of a derivative. So what's another notation for this? Well, we can use y prime. If the original function is called f of x, then the derivative of it would be called f prime of x. Or if the original function is called y equals something, then the derivative of it would be called y prime. Or if it's called g of x, the original function, the derivative would be g prime x. So what are other notations? Well, another notation is dy dx. That is the derivative of y, function y, with respect to x. Well, we can say that for a function that was called y, but can we say it also about a function that was called f? Absolutely. We can say if a function was called f, then df dx is the derivative of function f with respect to variable x. This is a very useful notation when we get to a certain parts of the course when you have multiple variables in a function, then you want to be clear about which variable you're differentiating the function with respect to. So if a function has variables m, n, and o, well, do you want to differentiate the function with respect to variable m, n, or o? So this kind of notation makes it very clear in situations like that. But nonetheless, it's the same at this point. Saying that or writing that is the same thing as that. Here we say f prime of x. Here we say df dx. Okay. Other forms of this notation can be d, just a d, and dx, and then here after that, f of x. That's the same thing as that, same thing as that, same thing as that, same thing as that. Okay, what are other notations? Well, we can have d, capital D, of f of x, right? And lastly, we can have derivative with respect to x of f of x. So different individuals in the history of mathematics have used different notations on this list. But here we're looking at notations that were used by different individuals, different famous mathematicians throughout the history of calculus, of course. So I want to box this set of notations. So you might be wondering, okay, we have all these various notations, but which ones are commonly used? So the common ones are, of course, this one, which you've already seen. Sometimes you see this one, sometimes, not very often, but that one. But definitely this one and that one and also this one are very common. So all these first 5 notations are very common, especially these two and that one. But these, you see them much less common in the books and in the way that are represented in classrooms. But they're common for a good reason, right? Because they're useful in the way they represent the derivative. And I just to be clear, so d and d over dx are called differentiation operators. Okay, so this is especially useful when you're attending a lecture and somebody talks about differentiation operators, then you know they're talking about those symbols. Okay, so let's talk about some notations that refer to the value of a derivative at some at some point. So here are such notations. So we can have f prime at a. We've already seen this in section 2.1, right? So this is the value. We're calculating the derivative at some value of x. So what is that this is going to give us? Well, we learned in section 2.1, and also we did a recap here. The derivative is the slope of the, let me move this up a little bit. The derivative is the slope of the tangent line to the function at a point. So this whole thing, when you calculate it, would be the slope of some tangent line at point A. What are other notations that would mean the same thing? Well, we talked about dy dx, so we can say dy dx, and then usually you see a vertical line like that, and you see x equals a. You might see that in a book or in a classroom or at a conference when somebody's talking about these. Or you might see something very similar, but a bracket rather than a vertical line. You might see dy dx, and then something like that rather than a vertical line, and then x equals a. Okay, so all of that. So these notations indicate the value of a derivative at some point, let's say x equals a, right? Because these are x equals a. But x can be anything, okay? So at this point, we get to an important note, and meanwhile, let me also draw a box around these, like that. So note that if f prime a, if that quantity exists, not that it would be undefined, but if it exists, then we say that the function f of x is differentiable at a. So if that exists, then the function is, and this is very important, that. So let's see an example, because we also want to discuss where is a function. So we've talked about differentiation again, in addition to section 2.1. We've discussed some notations. Now we want to see what do we mean when we say a function is differentiable at some point, or it's not differentiable at some point, because this is this begs the question, where is a function differentiable or not? Okay, as a matter of fact, let me add that. Where is a function differentiable or not? Okay, so we'll use an example to explain that. So suppose we have this example where we want to find where is the function f of x. Let's pick a simple function just to make sure that we understand the basics and the fundamentals of this. So f of x equals absolute value of x. Where is this function differentiable right? We can stop there, or we can say or not. Okay, let's ask both. A question can ask just where is the function differentiable, or where is the function differentiable, or it's not differentiable. Okay, so first of all, let's begin with the definition of the absolute value, right? So let's begin our solution. We say, let's begin with the definition of absolute value. Okay, which is, we know that absolute value of x is equal to x if x is greater than or equal to, or let's just take it as greater than 0, because at x equals 0, when we talk about differentiation at x equals 0, something happens here. So I'm just going to keep this. Normally we would say absolute value of x equals x if x is greater than or equal to 0, but for some reason, and I'll explain that in a second, I'll talk about why I want to leave the 0 out. So just x greater than 0 and equals to minus 6, of course, if x is some negative value, less than 0. Okay? So in each case of this function, we have to find the derivative of that function. So if we say if this is the case, if x is greater than 0 or something, a positive value, right, then move this up a little bit. Then we can say that f prime of x, and we're going to use for now, we're going to use the definition of the derivative. But as you'll find later, in later sections, the definition of the derivative is not the only technique we can use to find the derivative of a function. But for now, let's use the definition of the derivative. So f prime of x equals limit as h goes to 0 of x plus h minus x, let's see, minus x, because this is just x, right? So we're dealing with this. So let me actually, so if x greater than 0, then f of x is equal to x, according to this definition of absolute value, which we begin with, right? So we're dealing with this scenario, in which case then we substitute x with x plus h, and then minus x, of course, divided by h as the limit of all this difference quotient as h goes to 0. So what do we get here? We get limit of this difference quotient as h goes to 0 is x. You can simply remove the parentheses and you get x and minus x cancel each other out, and we end up with h over h. And then, of course, that leads to limit of 1, constant value 1, as h goes to 0, and of course we know that this is equal to 1, right? When we discussed the properties of limits, you remember that we said that limit of any constant value as anything, as say x approaches value, x approaches 0, it's equal to c, the constant value, right? So in this case, that constant value is 1. So we have that. So let's find the derivative of the absolute value function when x is some negative value, right? So that's the other side. That's this portion of the function. So we say if x is less than 0, right, or something negative, then of course we have, we're dealing with this. So we have f of x, which was the absolute value function, is equal to minus x. Okay, so now let's once again apply the definition of a derivative. We have f prime of x equals, I want to move this up a little bit, and then limit as h goes to 0. This time, when we replace x with x plus h, then this minus should distribute itself to the whole parentheses, right? So we have minus minus x plus h, then minus of this minus, right? Minus, and this time instead of x we have minus x, so minus x. Okay, so let's see. Right, so this is all of this over h. Okay, so now we have limit as h goes to 0. Let's distribute this minus x minus h minus minus x. It will be plus x divided by h. And then let's simplify here. Minus x and plus x cancel each other out like they did here. These two cancel each other out. And then we end up with limit as h goes to 0 of minus h over h. Then the h's cancel out, and we end up with, of course, limit of negative 1 as h goes to 0. What is that equal to? Of course, we know that is equal to minus 1. Right? So for each portion of the absolute value, we had to differentiate the function for each case when x is greater than 0 or x less than 0, and we get, of course, two different values. So what do we end up with? We end up with this result. We end up that thus so f prime of x, when f of x equals absolute value of x, f prime of x is equal to 1 if x is greater than 0, and it's equal to minus 1 if x is less than 0. Okay? So what we found is that the absolute value function is differentiable when x is greater than 0 and the value of the slope is equal to that. And when x is less than 0, then the value of the derivative of the absolute value function is equal to negative 1. Does this make sense? Absolutely. Let's take a quick look at the graph of the absolute value function. Right? I'm just going to draw a very simple and small graph here just to address the point. So if we draw a quick graph of the absolute value function, we have we have this kind of figure or graph. So we have that, and then we have that, this side of it. Like that. And this is f of x equals absolute value of x. So does this result, so the derivative is the slope of the tangent line to the curve, right? So for x greater than 0, of course, the value of the slope is positive 1, and that makes sense, right? We have, so this is, the slope of this would be, this line would be 1, 1, 1, right? Going that way, uphill. But for x values less than 0, the slope of the tangent line to that curve would be negative 1. And it's constant because these are straight lines, right? So that would be negative 1, negative 1, negative 1, and so on. So that's what we found. The slope of the line of the graph of this function is negative 1 when x is negative. It's positive 1 when x is positive. But what happens at 0? Did we forget that? No. So let's look at what happens at x equals 0. What is the derivative or the slope of the line at x equals 0? So we've done that. If x is greater than or equal to 0, greater than 0, right? We did that. We looked at this case where f with x, when x was less than 0, and also when x is equal to 0. So let's look at that. Right? So we have at x equals 0, then we have, so limit of x as x approaches 0 or of f of x equals limit of the absolute value function as x approaches 0, right, equals 0, right? We can just replace it and see that. That is 0. So at this point, then, f of the value of the function at 0, so the limit of the function as x approaches 0 is 0. Also, and the value of the function, absolute value function as 0 is 0. Okay, so what did we say when we talked about continuity of functions earlier in chapter 1, in those earlier sections? We said that if at any value of a function, if the limit of the functions are equal to each other, and those limits from the left and from the right are equal to the value of the function at that x value, then the function is said to be continuous at that point. Okay, so we can say that the function. Well, before we talked about continuity, let me finish this discussion about the differentiation. Here, what we've learned is that before we approach 0. So the limit of the absolute value function as we approach, let's write it out. This is pretty important. Therefore, the limit of f of x equals absolute value of x as we approach, as x approaches 0 from the left, and we did that with the h, with this description of the definition of the derivative, we did that. As x approaches 0 from the left, that limit is equal to -1. Okay, limit of this function is equal to -1, that limit. And when we approach the limit of that absolute value function as x approaches 0 from the right, is equal to +1, right? We did that. We just did that, and that's the result we got. But these two limits, so when we take the limits of the function from left to right, we end up with different values than the value of the function at x equals 0, which would be 0. So these values are not equal to each other at all. Okay, so therefore, so we can say that, let's just write it here, that so f of x is not differentiable at x equals 0. Very important. Why is this important? Because it says that if you find the limits from the left and right, and if they're different values, then the function is not differentiable or does not have a derivative at that value. That's the important result that we just arrived at. With this simple example, we arrived at that conclusion. So if you say a function is differentiable, then that means that at some point, then that means that the limit of the function at that particular point exists from both sides. The limits from both sides exist and they're equal to each other. Okay. The other conclusions we obtain from this example are these. Very important functions, and I'm sure those of you who will be taking higher and higher calculus classes, you will come across these conclusions again and again in the classroom. So here's an important conclusion, and it's of course a theorem. So let's say important theorem is that if a function f, if f is differentiable at some point, at some value, let's say some value a, then we can say definitely then f is continuous at a. F is continuous at a. Very, very important. So differentiation is a very a powerful and useful piece of information because it tells us that the function is continuous at that point. All right, so let me also box this. So that's one conclusion. So what does that mean instead at this, in terms of this example that we had then, right? We found that the absolute value function is not differentiable at x equals 0. It was only differentiable at x greater than 0 and less than 0. And we found the value of the derivative. But at x equals to 0, the absolute value function is not differentiable. Okay? So what does that mean? In terms of continuity, which is the next topic for us, we're kind of merging into that. It means that this function is not continuous at x equals 0. That's what it means, because it's not differentiable at x equals 0. Therefore, the absolute value function is not continuous at x equals 0. Okay, so that's one thing. And very, very much connected to this theorem, we should add to this, but the converse is not true. Very important. So this definition only works in this direction. If the function we know is differentiable at some value a, then the function f is continuous at a. But does this imply that if a function is continuous at a, then it must be differentiable at a? No, this is what this is saying. The converse is not true. Only we can say this in this direction, not vice versa. In other words, if a function is continuous at some point a, it does not mean that the function is differentiable at a. Okay? This is very important, not only to remember this throughout the series of calculus courses that you're taking, but also that the converse is not true. Very, very important. Okay, I don't want to put too much color on the page, but this is so important that I couldn't resist but also box this piece because they go together basically. Okay. All right. So then this brings us to the discussion that where or when a function would not be differentiable, because we just said that given this little graph of the absolute value function, we just pointed out that at this point, at x equals 0, the function is not differentiable. So that means the derivative of the function at this point does not exist. Okay? There is no slope of the tangent line at that point. There's no slope of this function does not have the slope of this function at this point x equals 0 is not defined. Therefore, its derivative, which represents the slope of the tangent line, is not defined. Okay? So what are different situations that this may be the case for a function, right? Where a function is not differentiable. We want to know that. I want to put all this information on a separate page because I don't think I can fit it all on this page. So I'm just going to move to page 5, even though I had a little bit of a space, half a page left there, but I don't think I can fit everything on that one, the rest of that page. So it's better to put all this information on one page. So we ask the question, we say, where then a function would not be differentiable? Okay, so we ask that. So here are the different cases that this might occur, but where then a function would not be differentiable. So we're saying that at that point the slope is undefined. Let me add that, i.e. The slope of the tangent line is undefined. Okay, that's what we're looking for. When is the function have this situation? So here are some cases. So case 1. So we say that in terms of the graph of the function, right? Let's talk about it visually, and then we get to the actual functions of a derivative later on in the course. But for now, let's make sure that we understand this concept graphically. So if the graph of a function f has a corner in it, so let me underline it. If it has a corner in it, then the graph of f has no tangent at that point, right? No tangent at this point. And therefore, f is not differentiable at that point. Therefore, f is not differentiable at that point. And I guess I should add, before I draw the graph, let me also add here, why is that? Why is it that when we have a corner point along a graph, then the function is not differentiable at that point? Here's why. Because each other. That's why. And in fact, that's it. That's what happened in this case. See, we have a corner point here, right? Right there. That's a corner point. So the limit from the left, as x approaches 0 from the left, was -1. And as we approach 0 from the right, the limit was equal to 1. So those numbers do not equal to each other. Therefore, the limit at that corner does not exist. So the function is not differentiable at that point, which means the slope of the tangent line at that point is undefined. Okay? That's why. And here is another example of a graph, that is. I'll just draw a small graph in this corner. So suppose, as another example, if we have like that, some function that might behave like this. And there are functions that behave like this. So, and this is the corner point. Right? So obviously, if you take the limit, regardless of what this function is, if you take the limit from to this point, a, as we approach a from the left, it's going to be some positive value, right? Something. But on this side, if we approach a from the right, then the slope is going to be something negative, right? Because the slope of the line, this curve is sloping downhill from left to right after point A. And the limits from approaching A do not agree from both sides. Okay, so that's another example of a corner. And why that function would not be differentiable at that point. So we might as well say it. So the function not differentiable at x equals a. Okay? All right, so what's the case 2? Case 2 is when we have jumps in the function or the graph of a function, or gaps. Let's look at that. So case 2, we say that if f is not continuous, that's what it means when we have a gap or a jump in the function or the graph. If f is not continuous at a, such as when we have jumps or a gap, or gaps in the graph, or jumps or gaps in the graph. You know, like piecewise functions, you have gaps usually in the graph. Then if function f is not differentiable at a. At a, right? So let's draw a little graph to show what might be a situation like that. So if we have something like this, like that, like that. So clearly at this point we have a jump and a gap, right, at that point. So once again, this function is not going to be differentiable at point A, right? If you take the limits from the left, approaching A from the left, what do you get? You get this value, right? If you approach it from the right, what do you get? You get that value, which is not, those values are not equal to each other, okay? So case 1 was when we had a corner. Case 2 was when we have a jump or a gap. Case 3, and that would be when the tangent line is vertical, right? We know the slope of a vertical tangent line is undefined. So that's the last case. So F we can say it's not differentiable at vertical tangent lines. Wherever the tangent line to the curve, to the function is a vertical line, then at that point the function is not differentiable. That's what this is saying. It's not differentiable at vertical tangent lines, since the slope of a vertical line, of course, does not exist. Vertical line is undefined, right? Undefined, or it doesn't exist. Defined. Okay, so here's some graph that might fall into this, or some function that might fall into this category. Suppose if we have a function that did this, right? Along this line, of course, the tangent line to the function at that point is a vertical line, right? So if we call that A, so that's a vertical tangent line. Okay, so that's the third case, where the function is not differentiable at x equals a. Okay, so I can emphasize this, what we said on the previous page. So please make sure that you remember this. It will serve you well. It'll take some time to make sure that you remember this and memorize it, but it's worth your time. Okay, that the fact that if a function is differentiable at some value a, then the function f is automatically continuous at a. Let me add that here, is automatically continuous at a. But of course the converse is not true. If you have a function that is continuous at some value, it doesn't necessarily mean that that function is differentiable at a. Okay. Okay, so we also want to talk about higher derivatives. So we say that if f prime is the first derivative of f, let's say, derivative of f, then guess what? F double prime is the second derivative of f, and so on. So you could have f triple prime, which would mean that's the third derivative of the function that you're finding, and so on and so forth, and so on. Okay, so that's just an allusion back to the notation discussion we had earlier. So other notations of the higher derivatives are as follows. So other notation basically means that we're learning a new language, right? We need to learn how to speak in this language. So we can have d dx of dy dx. So this is just like multiplication. It's exactly like multiplication. This is a very rare case of where notations mean multiplication. I say this because, remember, for, let's say, f of x, this doesn't mean that some f is being multiplied by x, right? This is just a name, f of x. It's the name of a function. It does not mean that they're being anything is being multiplied here. But here, this notation, these are being multiplied. So this times that gives us d squared y divided by dx squared. Okay, so that's one notation. So if you have this notation, which we mentioned above, so f double prime, that's the second derivative. If you take the derivative of this a third time, or prime, f double prime prime, then you have obtained the third derivative, so f triple prime. Okay, what else? Well, based on what we said here, can we have a third derivative and the notation follow the same pattern? Absolutely we can. So if we say d dx of d squared y divided by dx squared, what do you think this means? This means just multiply those things, entities. So d times d squared is d cubed y divided by dx cubed. So of course what this means is the third derivative of y with respect to x. As a matter of fact, let me say that here as well. So I forgot to write these. So here we have the second derivative of function y with respect to x. Okay, what is that then? That's the third derivative. It doesn't say with respect to which variable, but it's the third. So here, if you have only one variable, it doesn't matter, right? So it's obvious that this derivative, this third derivative, is with respect to that one variable. But if you have more than one variable in a function, that's mainly, you'll see that in definitely in Calculus 3 class, or Math 283, or maybe even in Calculus 2 you'll see that, and definitely you'll see that a lot in the differential equations in a course. So this is assuming that this function f had one variable, so this would be the third derivative. And here, of course, this is saying that what we're calculating is the third derivative of function y with respect to x. Okay. Do we have a generalized notation? Yes, we do. So if you have, suppose if you have, instead of f prime and this, we can substitute that with an n variable. So n is some positive value, some positive integer. So f of n of x is equal to dn y over dxn. So this is just the same things but generalized, where n where n is a positive integer. Okay, like that. Okay, so let's look at finding the derivatives of some functions using the definition of the derivative. Okay, and we're familiar with this, right? We've been using it since section 2.1. And also we want to, this particular question is asking us to state the domain. We haven't done one of these for a while, right? The domain. State the domain of the function and the domain of its derivative. Interesting. This concept of the domain was absent for a while. Now it's back with a force, right? With a vengeance. They want us to give the domain for the function and its derivative. Okay, we'll do that. So the function that we're dealing with here is this. Let's see, do we have, is this one. So the function g in terms of t is 1 over square root of t. Okay, so that's the function for which we want to find the derivative. Well, first of all, the domain of this is pretty obvious, right? Because t cannot be something negative, and t cannot be equal to 0, right? So t, therefore, the domain here, domain of this function is anything greater than 0, like that. Okay, so that's the domain of that. It was very simple for us to give that. Because of the square root, of course, we can't have any negative values, right? And because this is in the denominator, we can't have 0. So it should be positive number greater than 0, which is what this is. Okay. So using the definition of derivatives then, which we've applied many times before, so let's apply that here. We have g prime t equals the limit as h goes to 0 of 1 over square root of t plus h minus 1 over square root of t divided by h, of course. Okay. All right, so we need to take the common denominator up here in the numerator. Let's do that. So g prime. So by the way, it would be great if you pause the video at this point and solve this and find the derivative using the definition of the derivative. We've done this in the classroom, as you know, in the worksheets, and we've done it in section 2.1, so you should be pretty familiar with it. Just pause the video, finish this, and then come back to the video to compare your solution with this. I hope you do that, because that way you'll progress much faster. Okay? All right, so taking the common denominator there, we have the square root of t plus h times square root of t. So we have square root of t minus square root of t plus h, of course. All right, and all of that, I should have put that a little bit here, all of that over h. Okay, so now let's simplify. This is complex fraction, so we want to write it in a more simplified form. So let's do that. So g prime t, I don't think I can fit all this because I want to list every step. So I don't think I'm going to be able to fit all the solution on this page. So no worries, we're just going to go to the next page. And so simplifying that, we get square root of t minus square root of t plus h divided by h times square root of t plus h times square root of t. Right? This is just simplifying this complex fraction to this. All right? So I'm assuming that if you have any trouble going from here to here, you'll ask me. But let me, just in case, so the denominator here is, of course, 1. And the way we simplify this is we take the easiest way to simplify a complex fraction is multiply the terms that are farthest away from each other. This would be square root of t minus square root of t plus h times 1, and put that in the numerator. So 1, that 1, times, these are the farthest terms from each other, right? They are the farthest away from each other, from here to here. Multiply them, put it in the numerator. Divided by, now multiply the nearest terms by each other and put it in the denominator. So these are nearest each other, right? H times all of that. And that's why I get that, which is that. Okay? Very quickly we can simplify any complex fraction with this small rule. Okay? So multiply the farthest terms, the terms that are farthest away from each other, put them in the numerator, divided by, multiply the nearest terms by each other, put them in the denominator. Okay, so now we've learned how to simplify something like this, right? We have to rationalize the numerator. By the way, sorry about this. Let me add the limit notation here. The limit notation here, I left it out. And let me add that. So all of this, limit of that as h goes to 0. Then limit of all of that, all of this as h goes to 0. And of course, limit of all of this as h goes to 0. Okay. All right. So let's rationalize this. We get, let me move this up a little bit. So we get g prime t equals limit as h goes to 0 of square root of t minus square root of t plus h divided by h times square root of t plus h times square root of t multiplied by, let's rationalize the numerator, like that. Okay, so the numerator is going to simplify to a nice expression, right? This, so recall that x minus y times x plus y equals x squared minus y squared, right? Remember that relation, that shortcut formula? So this is that. In our case, x is square root of t, y is square root of t plus h. But it's x minus y times x plus y. It's the same format. So we get that. So in the numerator, we have, this is what we get according to this. We get g prime of t equals limit as h goes to 0. So we get square root of t squared minus square root of t plus h squared, right? Based on that. All of that divided by, oh yeah, that's correct. So all of that divided by all of that. This times that. So square root of t plus h times square root of t times square root of t plus square root of t plus h, close parentheses. Okay, so this is what I was talking about. I'm running out of space here. Let me move to the next page. Okay, so we need to simplify that. The numerator, it's very easy to see how that simplifies. Limit as h goes to 0. Square root of t squared is t minus square root of t plus h squared is this 2 and the square root cancel each other out. This power on the outside and the square root cancel each other out. And then we end up with t minus t plus h divided by all of that. Okay, so I just want to show every step. So if you get bored, sorry about that, but just to make sure that everybody can follow this. And now that minus distributes itself into this parenthesis. We get t minus t cancel each other out. Then we get minus h, right? Minus times h is minus h. So we have g prime t equals limit as h goes to 0 of minus h, right? This minus times h is minus h divided by all of that h times square root of t plus h times square root of t times square root of t plus square root of t plus h. Okay? All right, we're getting there, slowly, but we're getting there. So, of course, the h and h cancel each other out, right? That's nice, because then we don't have to worry about that h going to 0 and making everything 0. So g prime t equals limit as h goes to 0 of minus 1 in the numerator, of course, divided by all of that. Like that. Okay, so now that we got rid of that h, let's apply the limit, which means replace for h with 0. So we have minus 1 divided by, what do we get when we replace h with 0? We get square root of t. Here, there's no h, so we just less square root of t times square root of t again, because there's no h, plus, of course, square root of t plus h. H is 0, is square root of t. So this simplifies nicely, and we get g prime t is minus 1. Square root of t times square root of t is just t. Square root of t plus square root of t is 2 square root of t, right? This plus that is 2 square root of t. So what do we get? We get, let's put this, we already have the answer, but let's put it in a nicer way. So g prime t is equal to minus 1 divided by 2t square root of t. So this would be the derivative of the original expression using the definition of the derivative. Of course, we have to give the domain for this, right? The domain of the original function was parenthesis 0 comma infinity parenthesis, right, for that. So this is pretty much the same way. We can't have 0 for t, and because of the square root, we can't have anything, t being anything negative, right? So it's still, the domain is the same thing as the original function. So the domain is parenthesis 0 comma infinity there, okay, like that. And we also want to do that. So I hope this agrees with the solution that you have on your paper. If it doesn't, don't gloss over this. Just take a good look at all this and repeat this solution on your own again without looking at either solution. But just compare this with your original, with your own solution. Make sure you know what went wrong, why you didn't get the same answer, and then repeat it on your own without looking at this to see if you're going to get this result or not. Okay? Okay, so let's do another example. So once again, we're asked to use the definition of a derivative. To find f prime of x. And guess what? We'll have to find the second derivative as well. So f double prime of x. And then we have more work to do. So then graph f prime, and f double prime. Wow, this is packed, right? We need to find all of this. On a common, we have to graph all three on a common set of axes. Okay, let's do that. And here's the function, of course. So f of x, we are told that f of x is equal to x cubed minus 3x, which is not a complicated function, right? It's a pretty straightforward function. Okay, so using the definition of a derivative, then this is what we'll do. So we're going to find f prime of x first, then f double prime, And then we're going to graph f prime, f prime, and f double prime on the same set of axes. Okay? So first, f prime of x. Once again, we have limit as h goes to 0. So we're going to put x plus h for this, and then minus 3 times x plus h, right? Then minus f of x, which would be that. So let's do that. So in the brackets, we have x plus h cubed minus 3 times x plus h, right? Minus x cubed minus 3x. All of that over h. Okay? All right, so we got to simplify this, right? And we remember this is where those shortcut formulas that we were emphasizing that people commit to memory back in pre-calculus would come handy. It's not too late. If you haven't memorized them, it's not too late at all. You can do that now. So we have the x cubed plus 3x squared h plus 3x h squared plus, of course, h cubed. Then let's distribute the minus 3 into that parentheses. Minus 3x minus 3h. And then let's distribute this minus into all that. We get minus x cubed minus minus. Minus times minus is positive 3x. All of that divided by h. Okay, so let's simplify this expression a little bit, or as much as we can. Let's see. So we have the x cubed, that one, and minus x cubed cancel each other out. We have, let's see, what else we can cancel out. We have minus 3x, right? That one, and positive 3x cancel each other out. We have, do we have anything else that we can cancel out? Doesn't look like it. Okay, so let's write the rest of it down. So we have 3x squared h plus 3x h squared plus h cubed minus 3h, right? Divided by, you know what the nice thing about this is that the h is present in every term in the numerator, so we can factor it out and then cancel it with this h, right? So let's do that. So we're going to, so we say limit as h goes to 0. Let's factor the h out. 3x squared plus 3x h and plus h squared minus 3. Okay, let me double check this. Yes, that's okay. So over h, and of course the h's cancel each other out, and we end up with f prime of x equals, so all of this, so we have 3x squared plus 3xh plus h squared minus 3. And then now let's apply the limit, which means substitute for h with 0. What do we get? What do we end up with? These two terms drop out when you replace h with 0. We're going to get 3x squared minus 3. Right? So this is f prime of x. This is the first derivative. Okay. All right. So we're asked to find the second derivative. Let's do that. We repeat the same process that we did with the definition of the derivative, this time with this function, not with the original function. So we have f prime of x, f double prime of x, because it's the second derivative, right, is equal to limit as h goes to 0. Now this is our function, so we apply the definition of a derivative to that. So this will be 3, let's put all of this in brackets, 3 times x plus h squared minus 3 minus that whole thing. So 3x squared minus 3. All of this, of course, divided by h. Okay, so let's move to the next page. Like that. So now we're going to expand this to second power, then distribute the 3 into that to every term, and then combine the like terms and simplify things, right? So f double prime of x is equal to limit as h goes to 0 of 3 times, I'm going to expand that. So 3 times x squared plus 2xh plus h squared minus 3. Then let's distribute this minus into both terms. Minus 3x squared, minus times minus, positive 3. Divided by h. So let's distribute that 3 to everything. And by the way, we don't need this sheet anymore. All right, so like that. So we have 3x squared. 3 times 2xh is 6xh. 3 times h squared is 3h squared, right? Then minus 3 minus 3x squared plus 3. All of that over h. Okay, let's see if there's anything we can simplify here. We have 3x squared and minus 3x squared. They add up to 0. We have minus 3 and plus 3 adding up to 0. So we end up with f double prime of x equals that h times 6x. Well, we can factor these two, right? So this would be skipping one step. I hope you don't mind. So we only have these two terms. They both have an h in common. So let's factor it out. We get 6x plus 3h over h. And of course now these two h variables cancel out, and we get the f double prime x or the second derivative equaling 6x plus 3h. And of course now let's apply the limit. What do we get? We get f double prime of x is equal to, this term drops out as soon as you replace h with 0. Replace h with 0 as this suggests. That term drops out. You get 6x, right? That's the second derivative. Okay, so now they said that graph this. Graph the first function and the first derivative and the second derivative. So let's do that. maybe I can do it in the rest of this page that I have left. I'll try to fit it in. Okay, so let me just draw it in this corner. Like that. I want to increment these axes to, let's say, three increments, 1, 2, and 3. Same thing on this side, -1, -2, and -3. Right, so what was the original function? The original function was something cubed, right? So let's see where that was. Okay, here's the original function, x cubed minus 3x. So this is a polynomial. Polynomials, we know they are continuous. So if we factor that, so let me just put a line here. So original function was f of x equals x cubed minus 3x, which is equal to, let's factor x out, we get x squared minus 3, right? Then let's find the x and y intercepts for this polynomial. So we have if x is equal to 0, then for sure we have y equals 0. So the line for this function does go through the origin. So if x equals 0, then f of x equals 0. So one of the points, one of the intersection points, x and y intercept for this function is through the origin. How about this piece? So when x squared minus 3 equals 0, then x squared equals positive 3, right? X squared minus 3 equals 0, then move the negative 3 to the right side, it becomes positive. So solving for x is very easy. So x is going to be by the square root property, that we learned about in college algebra and pre-calculus 1, x equals plus or minus square root of 3, right? So what are these 2 points at? They are at negative square root of 3 comma 0 and positive square root of 3 comma 0. So these are all intercepts, that one, and that one, right? That's for that function. And of course we want to know, so let's draw it actually, let's do that. So the multiplicity, we learned about multiplicity in pre-calculus, right? The multiplicity of this factor of the polynomial is 1, which means at these points, at these x-intercepts, the line goes through the x-axis. It doesn't bounce back, it goes through. Remember what the multiplicity represented? If you have forgotten the idea of what multiplicity means in terms of a graph of function, please review it from your notes for pre-calculus 1, Math 126. We might have actually talked about that in college algebra. I'm sure we talk about it in pre-calculus 1 or Math 126, but I'm not sure if we do it. I think we do in college algebra or Math 124 as well. So please review that topic. And so because the power of this factor is 1, which is an odd value, and the power of x is also 1, which is an odd value, that means at these points of intersection, one is that's 0 comma 0. The other one, negative square root of 3. What is negative square root of 3? Let's just remind ourselves. So, well, let's calculate square root of 3. Square root of 3 is 1.73. So minus 1.73 roughly would be somewhere between -1 and -2, right? So that point is somewhere here. And positive 1.73 would be somewhere between 1 and 2. That would be somewhere here. So we know that this polynomial goes through the x-axis at those points. But the multiplicity tells us whether when passing through that point, whether it goes through to the other side or it bounces back to this side, to the same side that it comes from. Because the multiplicity is odd, which is 1 for both of those two factors, we know that the line at each point goes through the point. It goes through that, it goes through that to the other side, and it goes through that. So the only thing we have to know at this point is, okay, if it goes through that point, which side does it approach it? Does it approach this point? Does the graph of the function approach this point from up here or from down here? Well, let's pick a point. Let's pick -2 to tell us. If we substitute -2 in this function, and if it tells us the value of the function is something negative, then the line is coming from below. If we substitute -2 in that function, and it turns out to be something positive function value, then the line is coming from above, right? Because above this point, the function values are positive, right? Because of the y-axis is positive. Below this point, in this region, the y values are negative. So let's test -2. So testing x equals -2, we have f at -2 equals -2 cubed minus 3 times -2. Right? What do we have? We have -8 plus 6 or -2. It's negative. It's negative. So this is less than 0. So the line is coming from below, from where the function values are negative. See? All right, so now we know exactly how to draw this line. We're going to come up from below like this. Then we're going to come back down and go through this, and we're going to curve back up and go through that. So we'll do a rough estimate of where the line should go. So we do this, and then we do that, and then again we do that. Where it actually curves up and down, we will get to that in this course later. But for now, let's just roughly estimate where the graph line should go. So that's a rough sketch of x cubed minus 3x. Then they ask us to also graph the f prime. So what was f prime function? Let's bring it back. The f prime function is pretty easy function to graph. It's a quadratic function, right? Remember in college algebra and which is Math 124, and Pre-Calculus 1, which is Math 126, we talked about transformation of functions. Remember that? So we learned that once you know what the quadratic function, the basic quadratic function x squared looks like graphically, then you can easily transform it. So this 3 stretches the graph of the x squared vertically, right, like that, because of the positive coefficient here. And this minus 3 brings it down along the y-axis. So in other words, to graph f of x or f prime of x equals 3x squared minus 3, we want to graph this, right? All we have to do is drop. We know the quadratic function will go through that origin like that, right? That would be just f of x equals x squared. Because of this negative 3, we need to drop it down 3 units like that. So the vertex, instead of going through the origin for this, would go through minus 3, 0 comma minus 3 right there. And because of this, the impact of this positive 3 in front of the quadratic term would be to stretch the graph vertically, meaning the arms of the quadratic function graph would be closer to the y-axis. In other words, this is what it would look like. If x squared would be wider, so 3x squared would be closer. Those arms of the graph would be closer. And of course, so that's the y-intercept. And where would we need to know where would be the x-intercept? So let's find that out. So if 3x squared minus 3 equals 0, we're finding the x-intercept here. So then 3x squared equals 3, and then x squared equals 1. So x equals plus or minus 1, right? Therefore, the x-intercepts are 1 comma 0 and negative 1 comma 0. So we have, let's see. So that would be here and here. And this would be the y-intercept. Let's draw a line. I'll try to make my line as smoothly as possible, but I'm sure I'm not going to do as good of a job as a calculator or a computer. Here I come up and go through that like that. Okay, so that would be that. And of course, they ask us to graph the f double prime function, right? F double prime, let's put that here. And f double prime function we found, it's equal to 6x, right? That's a straight line. A straight line that goes through the origin. So we can roughly sketch it, something like this. So let me use a different color. It's going to be, because for every, if x is 1, y value is 6. If x is 2, y value is 12, right? So this is going to be a steep graph, a steep line, steep straight line right through the origin, like that. Okay, like that. So this is f double prime x equals 6x. And this is f prime of x equals 3x squared minus 3. And this is, of course, the black line graph here is original function, sorry. F of x equals, what was it? It was, right there. It's x cubed minus 3x, right? So as they asked us, we've graphed all three, the original function, the first derivative function, and the second derivative function, all on the same set of axes. So we have that. So there you have it. Okay? So before we close, I wanted to show you this on the computer as well. As I switch to the computer, your screen is gonna go dark for a couple of seconds. So don't mind that as I switch to the computer. I'll do it in a second. So let's see. All right. So there you have it. That's the graph of, you can see it on the left side of your screen, the functions I'm talking about, y equals x cubed minus 3x. Maybe I should change this, since I used, well, let's change these. So f of x, and this would be f prime of x, and this, of course, would be f double prime of x. F double prime of x equals that. So I wanted to make the notations, oops. Oh, it doesn't, it looks like it doesn't recognize that. Okay, so let me use it like before. It doesn't, it deletes the, okay, so g would be our first derivative, and let's make h our third derivative, second derivative, sorry. So there you have it, as graph on the computer. All right, thank you for persisting through this lecture as the other videos. And for now, have a nice day, and I hope to see you again in the next video.